for everyone to join. Giving a talk today on data-centric metaprogramming. Please welcome to the stage, Vlad.
Thank you. Thank you, everyone, for coming here. What is data-centric metaprogramming? Essentially, it's a way that you tell the compiler how you want it to represent your data, the data your program manipulates. Before we go on to the presentation, let me present myself. I'm a PhD student in the Scala team at EPFL. I'm soon going to graduate. I've worked on program transformations that make data representation more efficient. And particularly, I'm the author of the mini-boxing plugin. If you had a chance to look at it, it's a pretty cool way to transform generics, make them more efficient. And for example, collections can get 2-3x speedups out of that. It can go up to 20x. And I've worked a bit on the Scala compiler and on the Scala doc tool. If you know diagrams and if you use them, it's one of the features I added. OK, so first of all, I want to let you know that this is really research work. It's an avenue that I've been exploring. I'm not making any promises on behalf of the Scala team or on behalf of the Spark team. It's just an avenue that we'll see if things work out. Last traffic sign, please stop me at any point if you have questions. It's better that I keep you with me throughout the presentation. If you don't ask any questions, I'm going to assume you didn't get anything out of what I said. So better ask them. So we're first going to look at the motivation. And the motivation, we've seen it actually yesterday and today. It's mainly the fact that there's a performance discrepancy between data frames and RDDs. And of course, it's interesting to see what is happening. We have RDDs on one side and data frames on the other. RDDs are strongly typed, so you can integrate them with libraries in Scala, while data frames are dynamically typed and operate faster. Ideally, what should happen is to take the best qualities out of these two and have something in the middle that combines them. And this is the dataset API that Databricks guys are working on. But I would say it's, instead of being as fast as data frames, it's actually midway somewhere. And you might be wondering, why exactly is it midway? What is happening there? And what can we do to speed them up? So let's go back to a Scala example of object composition. You have the vector class, which is taken from the Scala collections library. And let's say you have an employee class, which is maybe defined to correspond to a table row. In that case, if you try to combine these two, you get a vector of employee. And as you can see, the vector is backed by arrays of pointers to employee objects. Why is this not efficient? Well, because we traverse with each step, with each employee we traverse, we have to dereference a pointer. So we lose locality, we have an overhead, and so on. Could this be improved? How many of you here can figure out a better representation? 1, 2, 3? I can bet more of you know the answer. It's simply doing the structured data approach, where we say we have columns, and each column is stored independently. So it's great to know that we have this, and it's more efficient, and it allows us to iterate faster. But unfortunately, vector of t is unaware of employee. So vector of employee, when we compose the two objects, is quite inefficient. And this is really not limited to vector. It affects all classes, and in particular for Spark, the pain point is functions. So we would like a structured representation with the column-oriented storage throughout the code, exactly like data frames do. Currently, the challenge is that we really don't have a proper way of telling the compiler, look, this is the object and you would better represent it differently. And this leaves us really with a choice of having safe RDDs or having fast data frames. And this is where my work comes in. I'm hoping to be able to address this in a way in the Scala compiler. So this is data-centric metaprogramming, which is a technique, a compiler plugin that allows you to tune the data representation in your program. It's open source, and it has a website that you can visit to see some documentation about it and a few examples. So let's look at the transformation. How does it work? First of all, when you think about a transformation that affects the way you represent data, you would have to split it in two different parts. One is the definition, which tells the compiler how to do it, and the other is the application. And the definition really can't be automated. It relies on information that the programmer has, that they would know exactly how the data is used and what is the best way to represent it. So it's probably the best person to say that is the programmer, whereas the application is quite repetitive, quite complex. So it would be much better if the compiler could take over and do everything automatically. Let's look at a definition for the data representation transformation that I showed you before. This is quite tedious, but I'm going to quickly walk you through the transformation definition. First, we say, what do we want to transform up there? And what do we want to transform to? Then we say how to do it. And finally, the last part of a transformation is how to run methods on the new representation. So for example, before we had a vector of employee.length. How are we going to run the length method, directly on the new representation? This is all the compiler needs to know. And then it can automatically apply this transformation to your code. And I'm not going to talk about how it does it. There's a paper that we published describing all the small details and all the technical problems that occur. I'm just going to focus on some challenges that I think will show you what exactly are the interesting things about this approach. First example is first challenge is the open world. So let's say we have again the vector and the employee, we combine them, and then we say, no, we're smarter. We're going to tell the compiler to use this columns-oriented structured representation. And then we leave for vacation for a week, and a colleague of ours defines a new employee class, which extends employee and adds a department. Well, the program the test suite is going to run. It's going to try to put the department. Well, whoops, it doesn't have the right tooling to do that. So if we look at this scenario, we can say that globally anything is possible. I'm going to say that locally, we usually have good control over our data structures. So things don't just pop up. A new subclass doesn't just pop up. So the options would be to make employee final, one option, and the other one would be to only use the transformation when we know for sure that in that piece of code, part of the code, we're not going to use anything but employee. And how can we achieve this? Of course, by using scopes, delimiting parts of the code that can use the transformation. This is a method that most Scala developers here would immediately understand. It's increasing the salary of everyone by a certain %. And if we wrap it in this transform scope, suddenly, instead of operating on vector of employee, it operates on the column-oriented storage. We don't need to do anything else other than mark this scope. And scopes can wrap a lot of things, can wrap statements, can wrap methods, can wrap entire classes. It's up to us what we want, which parts of the code we want to transform. And we're going to see how this relates to Spark in a few moments. But it's important that this technique these scopes are inline directly after parsing, so the definitions inside them can be seen outside as well. And we can use them to define local areas of the code where we can perform. It's safe to perform the transformation. Anything that comes in or goes out goes through our transformations, the ones we wrote. So we can reject values if we want to. Okay, so another challenge is the fact that there's a question of what is the best representation. So who thinks they know what is the best representation for the vector of employee? Good, nobody. Because it depends. It depends on what we do with the data. If we want to iterate a lot over this data, a column-oriented storage will be the most efficient way to store it. What if we do in-memory processing and we really don't have a lot of memory? We would like a very compact representation. So we would use a different way. Or what if, for example, we're communicating with a JSON server and we might decide we just want to store it in JSON right away. We don't want to convert to Scala objects, to a Scala vector with employees. We just operate directly on the JSON. So it really depends what is the best representation. And scopes allow us to really capture this property. Each part of the code can have its own transformation. For example, here I said the method will operate on the employee vector representation, on the column-oriented. Just switch the transformation, and it operates on a different data type, or on a different data representation. Again, switch it, we switch the transformation. We switch the data representation. So great, so far so good, but this opens up a new problem, the problem of composition. So we can have code that is left untransformed, like the original index salary method, or we can have it transformed with a certain new representation. This gives us a Cartesian product. What if original code calls transformed code and so on? So if we have original code calling original code, that's very easy, right? We don't need to do anything. On the other hand, if we have original code calling transformed code, or the other way around, we need to introduce coercions. We need to basically map between the two data representations and make sure the data is correctly transformed. What if another case is, what if transformed code calls another piece of transformed code, but it's transformed with the same representation? Well, this is a hard case, because what we would like to do is let the code, the two pieces of code, the two methods, or the two parts of the code interact without any coercion. So they should be able to pass data directly, even across separate compilation. This is a very hard problem. And even harder is what happens if you have two pieces of code with different transformations, and they start calling each other. Well, this is, again, a pretty complex situation. Fortunately, the compiler takes care of this, completely automated, warns you if things are inefficient. And I just wanted to point out that overriding makes the problem even more complex, because, for example, here's a printer trait and an employee printer that takes a vector of employees, right? As long as the employee vector class stays untransformed, the print method in the class implements the one in the trait. So far, so good. What if we wrap this whole employee printer into a scope that transforms its representation? Suddenly, the signature of print changes, and it's no longer implementing the signature in the trait. Wrong. The compiler takes care of all this for you, so you're never going to need to care about these things. You just define the transformation, that's all. Let's look at some applications now before we move on to Spark and see exactly how this could help Spark. Well, we've seen column-oriented storage. In my benchmarks, I've got 5x speedup over the vector of employee. Could be more or less depending. I also eliminated some boxing along the way. We could have, for example, retrofitting the value class status, which I'm not going to go into too many details. For Scala experts here, tuples are specialized, so they store primitives efficiently. But on the other hand, they're still heap allocated objects, so they could be optimized further. And in the case of a tuple of 2 integers, we can encode it as a long, so we don't allocate an object at all. This gives us 14x speedups on methods that use it. And of course, it lowers the heap requirements. Now, another example I wanted to show you, which starts to be related to Spark, is deforestation. Let's think we have a list of 1, 2, 3. We map it first incrementing 1, second doubling every element, and finally summing it up. According to the eager collections in Scala, this means after the first map, we have a list generated. After the second map, we have another list generated. And finally, at the end, we get the result we were looking for. So I would say the middle collections can be thrown away. I guess everybody agrees. So we could take this list class and say, well, we want to transform it into a lazy list. It might reorder some effects, but since our programmers have complete control over what is happening in that scope, it's safe to do this. And of course, it would accumulate the 2 functions and only apply them at the end when we need the result. And this is also 6 times faster. Finally, the interesting part, Spark. Again, research ahead, so this is just a research avenue that we're pursuing. So if we look at the optimizations Spark does to get these wonderful speedups, in data frames, it does deforestation. It does predicate pushdown, which means it's going to put the predicates before the joins, push them as close to the data source as possible. And it's going to do code generation for data frames, which means the code is specialized for the specific data. And functions that the selects and the things you do are also going to be specialized for the data representation, which is great. If you look at RDDs, on the other hand, they still do deforestation, so that's a great thing to have, but they don't do predicate pushdown, and they don't do code generation. So some of the things, this explains why they are a bit slower. Now, data sets, the new abstraction that they are developing, they do deforestation, they do predicate pushdown, they do code generation, and they do specialize the code. But there's a little problem. Functions that you define in Scala continue to operate on objects. As Michael called them in the presentation yesterday, they're opaque objects. So you need to create the object and pass it to the function and get the response back. OK, so let's see how this works. When you define a user function, you take an x and you return a y, right? 2 types. Actually, what happens is Spark has encoded data that it needs to decode to get you that object. And then it has to encode the return and put it again in serialized data. This is not great because it allocates 2 objects that just for applying the function. And I think we can eliminate these 2 by saying, all right, we have a modified user function that operates directly on the encoded data. There's no need to do this special object creation just to satisfy the function. And this is where the compiler comes in. In the compiler, I can modify the function and make it work directly on encoded data. And this probably will make things more efficient, but it's really nowhere near as simple as it looks on the slide. And I'm going to show you some challenges. Well, first of all, in some cases, you might have the transformation might not be possible. For example, we're calling outside method, a Java-defined method. Well, unfortunately, there's not much that it can do because it can't go into the bytecode and transform that function, that method. But we can issue compiler warnings. We can tell the user, look, it's not possible to transform your function, so it's going to be inefficient. It's going to be less efficient because you're making a call outside a transformed scope. And of course, the solution to fixing it, if you're writing it in Scala, is to simply put that method inside a transformed scope. And this is what the compiler is going to do. Just wrap a scope around that method, and it should work. These are all things that have been implemented in the miniboxing plugin. So there's quite a bit of chance that we might reuse some of the machinery. Another big problem is the internal API. So Spark internally relies heavily on the Scala library iterator, which of course requires materializing values, exactly like the vector did. And this will need to be replaced throughout the code base, so it doesn't operate on iterator, but on something that can be aware of the data representation. And it's rather complex to do that. Well, this will need some extensive rewriting, refactoring, I think. And finally, the last problem is automation. Well, the existing code that you have written already should operate immediately, should operate out of the box on the data. You should not have to rewrite anything. So the solution would be to adapt what I showed you, the data-centric metaprogramming, really to the Spark use case. And we would trade some of the generality, defining your own transformation and so on, for the simple fact that it just works. And it should do what you expect. It should boost performance in most of the cases. So it should have good common defaults. So where are we now? Well, I worked on a prototype lately. I would rather call it a hack rather than a prototype. So it's a modified version of the Spark core, and its RDDs can handle custom data representations inside them. It's a very limited prototype in that it only handles maps, filters, and flat maps. Whenever it goes outside, it just switches back to the object representation. So it's just more as a proof of concept. And large parts of the automation are still missing. Some of the stuff has to be transformed by hand, but it's possible to get the compiler to do it if that's going to be pursued. So one example that I can show you is simply taking a parallel collection, parallelizing it, and just doing a map and a filter and collecting. It's the most trivial example you can get. And with objects, it takes about 800 milliseconds, whereas the transform code operates at around 600 milliseconds. We don't get exactly the 2x speed up between RDDs and data frames, but we're reducing some of the differences here. And this can probably be pushed a little bit further as well. OK, so let's conclude. We have the object-oriented composition and the fact that we write functions that operate on objects that leads to inefficient ways of representing our data internally. A possible solution is data-centric metaprogramming, where we transform the opaque data, things that need to be according to a certain format, into either a structured data format or a flexible format. Is it possible? Yes, definitely, we can do it. Is it easy? No, not really. And I'm going to leave you with this question. Is it worth it? Thank you. And for more information, you can visit the website scalaildl.org. Thank you very much. Questions? Yes. Yes. So the
strategy, and shapeless takes care of the actual representation for me.
So the question is, so you will need to define your own transformations to benefit that, and I would say that's part of the automation problem. Hopefully not. It should have a sensible defaults, and you would just import something in scope, or could be done with macros to define the transformation. I haven't thought about exactly how to do this part. Any other questions? Okay, so thank you very much, and don't hesitate to find me on the hallways and ask. Thank you.